If you can see in the figure, we are dividing each trajectory into 4 driving states: our acceleration, deceleration, cruising, and idling. Filtering out the outlier of driving states, the second-by-second speed profile of the acceleration, deceleration are taken to the project level of moves to calculate corresponding emission. For this specific case, acceleration and deceleration have the features such as average duration, length, and emission rate. When adding the emission of 1 average acceleration and 1 deceleration, the emission factor per stop in grams can be computed. For this specific example, each stop caused approximately 49 grams equivalent CO2. Also, using the same method and the average cruising speed, the emission factors for cruising and then idling can be calculated. There is an alternative way to estimate emission factors, which is by using linear regression between total emission of each trajectory as dependent variable and 3 independent variables of number of stops, duration of cruising, and duration of idling. Comparison of the estimated emission from regression with true values calculated by moves shows almost 4% underestimation with a standard error of almost 292 grams, while resulted emission from all calculated emission factors show a less than 1% overestimation with a standard errors of 325 grams. Therefore, those estimations are quite reasonable. However, since the calculated emission factors provide a better result, in the rest of the presentation, emission factors, whenever I say emission factor, it means that the calculated factors. The reason for this difference has to do with the handling of oversaturated phases at the intersection. Since the analytical model is derived for deterministic and we have the constant arrival flow, and it provides a very good result when traffic conditions in the simulation are undersaturated. However, the simulation includes some random variation, so the intersection can sometimes get oversaturated when the arrival flow approaches the capacity, which contributes to increased error. In the next step, implementing the kinematic wave theory, we have developed an analytical model in order to estimate traffic parameters. The main assumption in this model are: the road section is homogeneous, the fundamental diagram is triangular, the intersection is undersaturated, which means that the arrival flow always are less than capacity. Arrival flow Q is less than capacity S. The intersection is isolated, which means that the links are enough long that the intersection is not being affected by any other intersection. Then, utilizing the geometry of the time-space diagram and having the information about the intersection capacity from the fundamental diagram, and also having the information of signal timing, we can estimate the number of vehicle stops as NS, and time spent idling as TID, and time spent in cruising state as TCR. Here, this is the equation that we have used to estimate the number of stops, where Q is the arrival flow to the intersection, S is the saturation flow, and R is the duration of red signal. And if the intersection is oversaturated during a signal cycle, the number of vehicles in the residual queue from the previous signal cycle, an R, will be applied. And this is the equation that we have used for the total time spent in idling state, where in addition to previous inputs, we have TACC here as the average duration of acceleration state and TDEC as the average duration of deceleration state. And finally, this is the equation that we have used to estimate total time spent in cruising state, where capital C is the length of signal cycle, VF is the free flow speed, Kj is the jam density, and capital L is the total length of segment. And in the case of such oversaturated condition, the correction factor of C should be applied. It should be noted that there is it should be noted that all of these relationships are based on traffic physics as represented in the geometry of time space diagram. So this represents a realistic and continuous relationship between the input parameters and traffic state variables that we want to know to estimate the emissions. Okay, calibration of a model is one of the essential parts for any modeling. If we are simulating a real network with real data, at this step we need to calibrate the traffic simulation. The two most important parameters in the simulation that should be calibrated based on real data are the free flow speed and acceleration properties. But since in this project a single hypothetical intersection has been simulated under various arrival flow and signal timing, there is no need for calibration. However, the same parameters should be used in the analytical model and the microscopic traffic model, MSON. So the both models are representing the same system. In the last step, which is the validation of results, using the results of traffic emission from MSON, the analytical model's results should be validated for different traffic conditions. We have defined 6 scenarios based on the variation of arrival flow and signal timing. In order to validate the traffic parameters estimated by analytical traffic model, as I'm going to show in next 2 slides, the estimates of driving cycle components, including number of stops and time spent in cruising and idling, should be compared with the calculated results by the MSON microsimulation. Also, to validate the emission volumes estimated using the integrated model, the emissions calculated by our model, which applies the emission factors to the analytical model's result, can be compared with the emission volumes calculated directly from the project level of moves using our vehicle's speed profile. Okay. As a validation of analytical model, here you can see the comparison of the number of stops estimated by using analytical model shown with the magenta line and the Amin simulation result. Each of the blue dots represents a period of simulation with a specific arrival rate. The horizontal axis is the demand to capacity ratio or saturation rate. So the intersection is fully saturated at the value of 1. Also, while the analytical model provides a smooth and continuous trend of variation because of the stochasticity in the simulation and the inclusion of some oversaturated phases in the averages over a specific period of time, the results of simulation do not present a perfectly smooth trend. The analytical model will tend to underestimate the number of stops if there is an error because an oversaturated cycle will result in more stops in the simulation. When simulation has more simulation is oversaturated, it results in more stops, number of stops. It can be seen that the longer size of signal cycle and higher ratio of green period to the cycle length, the trend of variation become more similar in both results, as you see in the bottom right corner graph. However, in a very short signal cycle with a very short green period, due to very small number of passing cars and number of stops, the trend cannot be seen in the Amin results, which are in the upper right left corner. Similarly, here you can see the trend of variation of time spent in idling and cruising, calculated by analytical model, which is the blue and red lines. Blue lines is for cruising time, and red line is for idling time. And they are compared with the results of simulation. As I said before, by reducing the capacity of intersection with the signal timing, the chance of oversaturated intersection increases, and it may cause more outliers in the simulation results. In this graph, duration of cruising state depends on the length of the links. If these links are too long, the effect of cruising will dominate and may affect other states. For this specific case, I have used a 0.4 mile link as an upstream link approaching the intersection, and a 0.1 mile link as a downstream link of intersection. Now having the number of stops and cruising and idling duration and implementing the impact emission factors, the total emission of each traffic state can be estimated. So here you can see the contribution of each driving state in total emission. Comparison of total emission generated by each driving state shows the higher saturation ratio, which is arrival flow to capacity, increase the contribution of emission of idling and stops, which is the summation of acceleration and deceleration, and decreases the contribution of cruising. On the other hand, the higher capacity of intersection, the less percentage of emissions caused by stopping and idling, and the more contribution from cruising in total emissions. In other words, as you see in two right-hand side figures, green line, which is the cruising emission, is very close to black line, which is the total emission. This means that the high contribution of cruising in total emission when we have a higher capacity, while in two left-hand side figures, the emission caused by idling, which is the magenta line, and the emission caused by stops, which is the summation of acceleration, blue line, and deceleration, red line, is one of the is even more than 2/3 of total emission. So this is a huge contribution of idling and number of stops in total emission. It should be noted that in this plot, in order to show the contribution of idling, the graphs are plotted based on emission per time, which is not very useful as emission to estimate the emission in our calculation. It's not very useful as we are using emission per distance. In general, it's the best to compare total emission per vehicle miles traveled, because increased congestion causes increased congestion changes the amount of time that vehicles spend on the road, but at least in the short run, it does not change the distance of their trip. Finally, here there are the results of emission estimations. The continuous green line represents the results of integrated traffic emission model, which provide a smooth and continuous emission estimation. The green dots are the estimated emission directly calculated by microscopic emission model of MOVES. Although the existence of any error in the estimated number of stops or duration of idling or cruising can directly affect the resulted emission estimation. However, the comparison of the estimated line and calculated dots, which are the dots are the true values estimations, true values which are estimated by MOVES and average over a specific period of time, verifies the result of integrated traffic emission model for our project, which is a single isolated intersection. It is actually very useful to have a model that shows with a simple continuous function how emissions will change in response to factors such as demand and traffic signal timing. This model can be used to help make comparative decisions between different traffic control strategies and intersection improvements. In fact, the great value of this method is that is based on aggregated traffic characteristics to provide aggregated emission estimation. We don't typically care about the emission from each individual vehicle. Instead, it's more important that we design streets and intersections to perform well as a system. Therefore, this model is a step toward improving our ability to access total emission associated with the traffic in street networks. As the conclusion, the integrated traffic emission model can simply provide a reliable estimate of traffic emission based on emission factors calculated from a sample of detailed data, and the analytical modeling approach allows us to compare the continuous range of traffic conditions without the need for extensive data collection and repetitive simulation. And emission factors are valid as long as there is no major change in driving behavior, which is a very good point. So we don't need to recalculate the emission factor very often. And finally, while the average speed-based macroscopic emission models estimate emission of large urban networks without considering the traffic condition, and microscopic emission modeling is not applicable to wide networks, integrated traffic emission model estimates traffic parameters and emission more accurately. In the next step, we are going to expand our work to the network level, and we are trying to estimate the number of stops, duration of idling and cruising with a sample network using a fundamental diagram information. And using these parameters, that we are going to estimate the network level of traffic emission. Thank you very much. I will be happy to answer your question. Few minutes. Good. It seems that nobody has any question.